Now we'll talk about powers and roots. In order to discuss the idea of an exponent, let's first think about multiplication. Multiplication is really a way of doing a whole lot of addition at once. So let's think about this. If I were to ask you to add 6 4s together, no one in their right mind would sit there and add 4 plus 4 plus 4 plus 4. No one would do that. Of course, what you would do is simply multiply 4 times 6. It's just important to keep in mind that in any act of multiplication, really what you're doing is a whole lot of addition at once. Much in the same way, exponents are a way of doing a whole lot of multiplication at once. If I were to ask you to multiply 7 3s together, we wouldn't write 3 times 3 times 3. We wouldn't write out that long expression. Instead, we would write 3 to the 7th. Fundamentally, 3 to the 7th means that we multiply 7 factors of 3 multiplied together. So it's a very compact notation to express a lot of multiplication at once. Now I hasten to add, the test will not expect you to compute that value. It's not going to be a test question, calculate 3 to the 7th. That's not going to be on the test. But you will have to handle that quantity in relation to other quantities. For example, use the laws of exponents to figure out 3 to the 7th and that whole thing squared, or multiplying it by 3 to the 5th, or dividing it by something. You have to use it, but you're not going to have to calculate its value. Symbolically, we could say that b to the n means that n factors of b are multiplied together. So this is the fundamental definition of what an exponent is. And right now I'll just say b is the base, n is the exponent, and b to the n is the power. Now this is a good definition for now, but as we'll see, this definition is ultimately somewhat naive, and we're going to have to expand it in later modules. And why is it naive? Well, if you think about it, how many factors of b that are multiplied together? This means that n is a counting number. That is to say, it is a positive integer. And so this definition, this way of thinking about exponents, is perfectly good as long as the exponents are positive integers. But as we will see in upcoming modules, there are all kinds of exponents that are not positive integers. We'll talk about negative exponents and fraction exponents, all that. Let's not worry about that in this module. In this module, we'll just stick with the positive integers, so we can stick with this very intuitive definition of what an exponent is. First of all, notice that we can give exponents to either numbers or variables. We have already seen variables with powers in the algebra module, especially in the videos on quadratics where you have x squared. Notice that we can read that expression either as 7 to the power of 8 or 7 to the 8th. Either one of those is perfectly correct. Notice that we have a different way of talking about exponents of 2 or 3. Something to the power of 2 is squared and something to the power of 3 is cubed. So we would rarely say something to the power of 3, and we would never say something to the power of 2. That just sounds awkward. We would always say that thing squared. If 1 is the base, then the exponent doesn't matter. 1 to any power is 1. And in fact, that expression, 1 to the n equals 1, that works for all n. That's not restricted to positive integers. That actually works for every single number on the number line. So every single number on the number line, if you put it in for n, 1 to the n equals 1. So that's an important thing to remember. If 0 is the base, then 0 to any positive exponent is 0. So 0 to the n equals 0 as long as n is positive. And in fact, this is true not only of positive integers, it's also true of positive fractions. It's true of everything to the right of 0 on the number line. So don't worry about 0 to the power of 0 or 0 to the power of negatives. You will not have to deal with this on the test. That gets into either illegal mathematics or other forms of mathematics that we don't need to worry about. So that's just going to be something we can ignore. An idea we have already discussed in the integer properties and algebra lessons: if an exponent is not written, we can assume that the exponent is 1. We talked a little about this in prime factorizations, and we talked about this again in the algebra module. Another way to say that is any base to the power of 1 means that we have only one factor of that base. So 2 to the 1 is 2. 2 squared is 4, 2 cubed is 3 factors, so that's 8. So again, we're using the exponent as a way to count the number of factors we have in the total product. What happens if the base is negative? What if we start raising a negative number to powers? Well, negative 2 to the 1, of course, would be negative 2. Negative 2 squared, that's negative times negative, that would be positive 4. If we multiply another factor of negative 2, positive times negative gives us a negative 8. Multiply another factor of 2, we get negative 8 times negative 2 gives us positive 16. Multiply another factor of 2, we get negative 32. And notice we have kind of an alternating pattern here. We're going from negative to positive, negative to positive, negative to positive. So we get a negative to any even power is a positive number, and a negative to any odd power is negative. We'll talk more about this in the next video. This has implications for solving algebraic equations. For example, the equation x squared equals 4 has two solutions, x equals 2 and x equals negative 2, because either of those squared equals 4. By contrast, the equation x cubed equals 8 has only one solution, x equals positive 2. If we cube positive 2, we get positive 8, but if we cube negative 2, we get negative 8. Notice also that an equation of the form something squared equals a negative has no solution. So for example, x minus 1 squared equals negative 4. Well, there's no way that we can square anything and get negative 4. So that's an equation that has no solution. But we could have something cubed equals a negative. That's perfectly fine. If something cubed equals negative 1, then that thing must equal negative 1, and then we can solve for x. Finally, just as it is important to know your times tables, so it is important to know some of the basic powers of single-digit numbers. So here's what I'm going to recommend memorizing and knowing. And it's helpful actually to multiply these out step by step to help you remember them. First of all, I'll recommend knowing the powers of 2 up to at least 2 to the 9th. And why all the way up to 2 to the 9th? Well, we'll be talking about this more when we talk about some of the rules for exponents. But again, very good actually to practice once in a while. Just keep on multiplying by 2 and get all these numbers just so that you verify for yourself where they come from. Know the powers of 3 up to at least 3 to the 4th, the powers of 4 up to the 4th, the powers of 5 up to the 4th. Again, multiply all these out from time to time just to remind yourself of all these so that you really can remember them very well. And then you should know, of course, the squares and the cubes of everything from 6 to 9. And why would you need to know all these? Well, again, we'll talk about these more when we talk about some of the rules of exponents. And of course, know all the powers of 10. That was discussed in the multiples of 10 lesson. It's very easy to figure out powers of 10. You're just adding zeros, or for negative powers, you're putting it behind the decimal point. Fundamentally, b to the n means n factors of b multiplied together. That is the fundamental definition of an exponent, and it's very good as we move through the laws of exponents to keep in mind that fundamental definition of an exponent. 1 to any power is 1. 0 to any positive power is 0. A negative to an even power is positive. A negative to an odd power is negative. An equation with an expression to an even power equal to a negative is no solution, but an odd power can equal a negative. And finally, know the basic powers of the single-digit numbers. In this video, we're going to talk about some different patterns of exponential growth, the different patterns that we get when we have powers of different kinds of numbers. So the first thing I'll emphasize in this video is not about the exact calculations. I would say worry less about the exact values of the number. What's important to get from this video are the patterns, what's getting bigger, what's getting smaller, and when. And it's very important to be aware of these properties in a variety of questions. The test absolutely loves these patterns and asks about them in several different ways. For different bases, we will look at what happens to the powers when the exponents increase through the integers. So case 1, we're going to have a positive base greater than 1. We've already seen this in the last video. I'll use powers of 7 as an example. 7 to the 1 is 7. 7 squared is 49. I mentioned in the last video that 7 cubed is 343. That's a good number to know. And then as we get to higher powers of 7, these are not numbers that you need to know. I'm showing you these higher powers only to emphasize that exponential growth starts to get very big very quickly. So this is one good idea to keep in mind, that if you have a base greater than 1, and especially if it's greater than 5 or greater than 10, then what's going to happen as you start raising powers of it, it's going to get inconceivably big very quickly. So the big idea here is a positive base greater than 1, the powers continually get larger at a faster and faster rate. That's very important. So that's pattern number 1. That's the pattern when we have a positive base greater than 1. Suppose we have a positive base less than 1. Okay, well this is interesting. Let's say 1/2, for example. So 1/2 to the 1 is 1/2. 1/2 squared is a quarter, then an eighth, then a 16th. Notice that things are getting smaller and smaller and smaller. We get down to 1 over 128, and finally down to 1 over 256. So we've gotten very, very small at this point. So much as in the first case we got big very quickly, now we're getting small very quickly. It's possible for higher exponents to produce smaller patterns. So in other words, as we raise the exponent higher and higher, it's possible for the overall power to get smaller and smaller and smaller. And so this is an important thing to keep in mind. Numbers, when we have a base between 0 and 1, a positive base less than 1, then we're going to be following a very different pattern for exponential growth than if the base were more than 1. Now, even more interesting, let's talk about a negative base less than -1. So this is a number that is negative and it has an absolute value more than 1. So for example, let's just take 3. 3 to the 1 is 3. 3 to -3 squared is +9. -3 cubed is -27. -3 to the 4th is +81. -3 to the 5th, we talked about this a little in the last video, 3 to the 5th is 243, so -3 to the 5th is -243, and -3 to the 6th is +729. So again, notice we have this alternating pattern. We saw this alternating pattern in the previous video. The absolute values of these powers are getting bigger each time, but the positive and negative signs are alternating. So this combines the idea of case 1 with continuously getting bigger. What's continuously getting bigger are the absolute values of the numbers, but the actual number itself is flip-flopping between positive and negative. So we get a big positive, then a bigger negative, then a bigger positive, then a bigger negative. It's going back and forth like that. So you can imagine these wild jumps on the number line from a very large positive number to a very large negative number. That's what's happening when we raise a negative base less than 1 to these powers. Finally, the last case, a negative fraction. That is to say, a negative base between 0 and -1 and 0. So this would be a number that is negative and has an absolute value less than 1. It is between -1 and 0. So let's take -1/2. -1/2 to the 1 is, of course, -1/2. -1 squared is +1/4. -1 cubed is -1/8. -1 to the 4th is +16. -1/2 to the 5th is -32. -1 to the 6th is +64. -1/2 to the 7th is -128. And then +1 over 256. So notice, similar to what was happening in case 2, the absolute values are getting smaller and smaller, but we're flip-flopping again between positive and negative. So we're getting closer to 0, but we're getting closer to 0 by jumping back and forth above 0 and below 0. We're approaching 0 by this kind of skipping pattern. going above it and below it and getting closer each time. Notice that as the exponent increases, whether the power gets bigger or smaller depends on the base. So if we ask the question, is x to the 7th greater than x to the 6th? Well, there's no clear answer. It would be true for positive numbers greater than 1 and false for negatives. Also, if x equals 0, x to the 7th would equal x to the 6th, which would be 0, and that's also a no answer. X to the 7th would not be greater than x to the 6th if it's equal to x to the 6th. Now consider this question. If x is less than 1 and x is unequal to 0, is x to the 7th greater than x to the 6th? Well, we have to consider what happens in different cases. First of all, it's very easy to think about what happens with the negatives. If x is negative, then x to the 7th is negative and x to the 6th is positive. And any positive is greater than any negative. So therefore, we're going to get a no answer to the question. We're going to get a clear answer of no. X to the 6th is definitely going to be bigger if x is negative. What if x is a positive number between 0 and 1? So these are the only positive numbers allowed, the positive numbers between 0 and 1. Well, if we square, say, 2/3, square that, we get 4/9. If we cube it, we get 8/27. Now notice that 4/9, 2/3 is above 1/2. 4/9 is slightly below 1/2. It's above 1/4. 8/27, well, 8/27 is definitely less than 1/3. 4/9 is greater than 1/3. 8/27 is less than 1/3. Then we get to the 16/81. That's actually less than 1/4. And what's happening is that these numbers are getting smaller and smaller. And this is what we've seen in these powers. This is our case 2 above, where we have positive numbers less than 1. As we raise higher and higher powers, we get smaller and smaller numbers. So we can definitely say that the powers are getting smaller. So if we extend this pattern, of course, x to the 6th is going to be bigger than x to the 7th. This is also going to produce a no answer. And it turns out that the answer to the question is a consistent no for every x allowed. So we can give a definitive answer of no to this question. In this video, we discussed the patterns of exponential growth, how increasing the exponent changes the size of the powers for different kinds of bases. In this video, we can start talking about some of the laws of exponents. Now, these are really big, these are really important on the test, because these are patterns that are true for all numbers. The first situation concerns multiplying two powers. We have a to the n times a to the m. Now, one thing that happens is folks get stuck thinking about these things very abstractly. And they force themselves to memorize a bunch of abstract rules, and then it's hard to remember which rule is which, and they get themselves all confused. I'm going to urge you to think in terms of the fundamental definition of what an exponent is. If you can go back to the fundamental definition of what an exponent is and understand the law from that perspective, then you will really understand it. So, in order to understand multiplying two powers, let's think about numbers. If I have 9 to the 5th times 9 to the 3rd, well, think about what that means. What fundamentally is 9 to the 5th? 9 to the 5th fundamentally means 5 factors of 9 multiplied together. And 9 cubed means 3 factors of 9 multiplied together. So in other words, I'm multiplying something with 5 factors of 9 times something with 3 factors of 9. And of course, when I multiply, I can just put all those factors together. And of course, what do I have there? How many factors? Well, I have 5 plus 3. I have 8 factors of 9. So of course, that equals 9 to the 8th. So clearly, 9 to the 5th times 9 cubed equals 9 to the 8th. Now think about that a little more abstractly. We have 7 to the m times 7 to the n. The first contains m factors of 7 multiplied together, and the second contains n factors of 7 multiplied together. So if I just multiply all the factors of 7 together, what I'm going to get is a whole string of factors of 7, and there will be m plus n factors of 7 in that string. And so what this means is that this should equal 7 to the m plus n. Now we can treat this entirely in variables. If I have a to the m times a to the n, think about this again. The first contains m factors of a, so I have a times a times a, m times. The second one contains n factors of a, so I have a times a times a, n times. I multiply them all together, I'm going to get this long string of factors of a, and the number of factors of a in that string will be n plus m. So, in other words, we can just add those two numbers. That's the new exponent for a. And that right there is one of our laws of exponents. Multiplying two powers of the same base means that we can add the exponents. Now the next question concerns what happens when we divide powers. Again, don't think in terms of just an abstract law. Let's go back and think this through in terms of the fundamental definition of an exponent. If you understand this law from the perspective of fundamentally what is an exponent, then you will really understand it. So I'm going to suggest starting with numbers first. Let's say 12 to the 7th divided by 12 cubed. How would we figure this out? Well, 12 to the 7th has to be 7 factors of 12 multiplied together. We have to have that in the numerator. In the denominator, we're going to have 3 factors of 12 multiplied together. So we're going to have something like this. Well, obviously, we're going to get some cancellation here. We're going to be able to cancel 1, 2, 3 factors of 12 in the numerator and denominator. So everything in red there, all that cancels. And of course, when you cancel, it just becomes 1. So it's 1 times everything else. And so we are just left with 4 factors of 12. And that's 12 to the 4th. So 12 to the 7th divided by 12 to the 3rd equals 12 to the 4th. Right there, that suggests the rule. We'll make this a little more abstract. 12 to the m over 12 to the n. Well, here we're going to have a fraction, and in the numerator of the fraction we have m factors of 12. In the denominator we have n factors of 12, and we're going to assume that m is greater than n, at least in this video. This means that n factors of 12 will cancel, so all the factors in the denominator will cancel, and that will remove some of the factors from the numerator, and what will be left in the numerator after we remove those n factors that canceled will be left with m minus n factors of 12. And so what we're going to be left with is just 12 to the m minus n. Now we can do that entirely in variables. Think through it in variables. We have a to the m divided by a to the n. So this is a fraction. In the numerator, we have m factors of a. In the denominator, we have n factors. For this video, again, we're going to assume that m is greater than n. So all those factors in the denominator will cancel when we take the m factors in the numerator and remove the n factors that cancel. We're going to be left with m minus n, and that's going to be the exponent of a. And right there is our second law of exponents. When we divide powers of the same base, this means that what we have to do is subtract the exponents. At this point, we can talk about a zero exponent. So far, we've talked only about positive integers, but now we can expand to 0. What does a to the 0 mean? Using the division law we have just discussed, it wouldn't be hard to create a zero exponent. In other words, all we'd need is to divide two powers that have the same exponent, and the subtraction will lead to 0. So, for example, if I divide a cubed divided by a cubed, according to the law of exponents that we just have derived here, this means subtract the exponent. This should be a to the 3 minus 3, which is a to the 0. But, of course, anything over itself must equal 1. A to the 3 over a to the 3, that's something over itself. That has to equal 1. So a to the 0 equals 1. Now, is this law always true? Notice the only assumption we made in that argument was that the division was legal in the first place. Obviously, it wouldn't be legal if a equals 0, but it would be legal for every other value. So we can say if a is unequal to 0, then a to the 0 equals 1. And as far as what happens with 0 to the 0, don't worry about that. That's something we get into in more advanced areas of mathematics. You do not need to worry about that for the test. But you do need to know that for anything other than 0, raising it to the 0 power is equal to 1. The last scenario we will discuss is when we have a power to a power. So we have a to the m and that whole thing to the n. And again, we're going to think this through in terms of the fundamental laws of exponents. If you know this in terms of the fundamental laws of exponents, you will understand it much more deeply. So let's start with numbers. 6 to the 5th and that whole thing cubed. Well, of course, 6 to the 5th, what that means fundamentally is 5 factors of 6 multiplied together. So we have 5 factors of 6 multiplied together in the parentheses, and we're cubing that. Well, what does it mean to cube something? To cube something means that we multiply it by itself 3 times. So we take that parenthesis, and it's that parenthesis times itself 3 times. So that would be expanded out what we mean with all the factors. Well, how many factors do we have there? Well, we have 3 parentheses, and each one has 5 factors in it. So that means when we multiply it all together, we must have 3 times 5, or 15 factors of 6. And so, of course, it would be 6 to the 15th. Now we'll do this a little more abstractly. Inside the parentheses, we have m factors of a. When we raise this to the power of n, we have n different sets, each with m factors of a. In other words, we have a total of m times n factors of a. And so that means that the exponent has to be a to the m times n. And that's our law of exponents. Raising a power to a power results in multiplying the exponents. So far, the law of exponents we have reviewed here are, so product of 2 powers means add the exponents, quotient of 2 powers means subtract the exponents, a to the 0 equals 1, and power to a power means multiply the exponents. And once again, please do not memorize these in an abstract rote fashion. Please understand the arguments. Going back to the fundamental definition of what an exponent is, understand those arguments and think through them, and then you'll really understand why they're true. I also want to mention some common mistakes with exponents. It's good to know not only the patterns of what is true, but also the typical mistake patterns, because the test always likes to test those particular mistake patterns. First of all, notice that all these laws work if the bases of the 2 powers involved are the same. We cannot apply any of these rules if the bases are different. So for example, if we have things like this, we absolutely cannot apply a law of exponent. 2 cubed times 3 to the 5th, that does not equal 6 to something. If we have 12 to the 7th divided by 4 to the 5th, that does not equal 3 to the something. So there are no laws of exponents that are relevant if the bases are different. Another mistake folks make when working quickly is to carry the operation on the powers to the exponent itself. In other words, when they're multiplying the powers, people make the mistake of multiplying the exponents. Okay, that's a very common mistake when people are working quickly. And of course, the correct thing to do is add the exponents. Or when people are dividing powers, they mistakenly divide the exponents. And again, the correct thing to do is to subtract the exponents. And this is a really good one, raising a power to a power, because there's all kinds of mistakes people can make. So either they mistakenly raise the first exponent to the second exponent, so that's one kind of mistake people can make. Another kind of mistake that people can make is they confuse this with the product of powers laws, and they mistakenly add the exponents. So that's another kind of mistake people can make. And of course, what you're supposed to do here is you're supposed to multiply the 2 exponents. So 61 to the 14th, that would be the correct answer. Finally, there is no law for the sum or difference of powers. So if we're adding 3 to the 4th plus 3 to the 7th, or 5 to the 8th minus 5 squared, there is no fixed pattern for this. There's no single law of exponents. In a couple lessons, we'll learn how to use factoring out to simplify this kind of situation. So in other words, we may see this, but it's not a simple law of exponents. It's a somewhat more sophisticated trick that we'll discuss in a couple videos. Overall, remember, as in any branch of mathematics, understanding means knowing not only the rule itself, but also why it is true and what the common misunderstandings are. So that's a really deep understanding if you can understand from that perspective. In summary, we talked about these laws of exponents, we talked about some common exponent mistakes, and we talked about how there's no exponent law for the sum or difference of powers. At this point, we are ready to talk about the idea of negative exponents. So notice so far in these lessons, we've discussed only positive integer exponents and 0 as an exponent. So really we've kind of stuck with this idea that an exponent means the number of factors multiplied together. And so we think of the exponent as something we can count. Now we're moving a little bit outside of that. We're expanding the definition where the exponent can be a negative integer as well. And we have to ask ourselves exactly what would this mean? What would it mean to have a negative integer as an exponent? We had b to the negative 3. What on earth would that mean? Well, as mathematicians often do, we will take a pattern that we already know and understand and extend it to cover something not yet covered by the rules. This is something that happens in mathematics over and over again. In this particular case, we know the division rule for powers. That's something we've talked about in the previous video. We know that if we made the denominator exponent smaller and then the denominator exponent bigger and the numerator exponent smaller, then we would get a negative result for the subtraction, and that would give us a negative exponent. Let's look at a numerical example with a higher power in the denominator. So, for example, suppose we had 13 to the 4 divided by 13 to the 7. Well, the power in the denominator is clearly a larger power. Well, if we just follow the division of the power pattern for exponents, of course that tells us to subtract the exponents, we'd get 13 to the 4 minus 7, or 13 to the negative 3. All right, that's one way to approach this. Now let's go back and think about this in terms of the fundamental definition of an exponent. The fundamental definition of an exponent is that 13 to the 4 means that we're multiplying 4 factors of 13 together. And similarly in the denominator, we'd have 7 factors of 13 multiplied together. And so what we have here, of course, we're going to get some cancellation. We're going to cancel 4 of those factors of 13 in the numerator and the denominator. They're going to cancel. When we cancel, we're going to be left with 1 in the numerator. And we're going to have 3 factors of 13 in the denominator. And of course, this would be 1 over 13 cubed. Now compare those two results. One way of thinking about it, we got 13 to the negative 3. Another way of thinking about it, we got 1 over 13 cubed. If these two equal the same thing, they must equal each other. And this suggests that b to the negative n equals 1 over b to the n. So that is the exponent rule. That is the rule for negative exponents. And this is one way to think about it. Here's another way to think about it. Any negative number can be written as 0 minus the absolute value of that number. For example, we could write negative 3 as 0 minus positive 3. In general, negative n, we could write that as 0 minus n. So this means that b to the negative n, we can think of that as b to the 0 minus n. Well, if we have subtraction in the exponents, that means divide the powers. That must mean b to the 0 divided by b to the n, and of course b to the 0 is 1. And so this would be 1 over b to the n. So this is another way to think about why b to the negative n equals 1 over b to the n. Here's another way to think about it. It's good to have as many ways to think about this as possible because it's a somewhat anti-intuitive idea, thinking about negative exponents. It's really good to have a variety of ways to make sense of it. Imagine a sidewalk of exponents. So notice that every number on the top equals, the power on the top equals the output on the bottom. So that's true for every box here. And as we move to the right, what's happening is we add 1 to the exponent. So the exponent is increasing in the green row at the top, and we multiply by a factor of 2 in the bottom row. So to go from 1 to 2 to 4 to 8 to 16, each step we're multiplying by 2. That's what happens when we move to the right. Each step to the left, we subtract 1 from the exponent, and we divide by 2 in the bottom row. So if we start at 2 to the 5th and 32, as we start taking steps to the left, we're subtracting 1 from the exponent, and we're dividing the purple number in the bottom by 2. What would happen if we walk to the left of 0? So here's our sidewalk again, but we just extended it to the left past 2 to the 0. Well, again, going to the left, the exponents go down by 1 each step in the top row, and the numbers get divided by 2 each step in the bottom row. So in the top row, that exponent would go down from 0 to -1, and we would divide 1 by 2, so we would get 1/2. 2 to the -1 equals 1/2. Now take another step. That would be 2 to the -2 equals 1/2 divided by 2, which would be 1/4. Take another step. 2 to the -3 and 1/8. Then 2 to the -4 and 1/16. And you see this same pattern continues perfectly for both the positive and negative numbers. In many ways, the exponent rule fits with the other exponent patterns very, very well. And the more you appreciate how they all fit together as a seamless whole, the more you will really understand this rule. So the rule, of course, is b to the -n equals 1 over b to the n. So another way to say this is a base to a negative power is the reciprocal of that same base to the positive power. This means that a negative exponent on a fraction will be the reciprocal to the positive power. So I have the fraction p over q to the -n, that will equal q over p to the positive n. That's a really handy shortcut to know on the test. A negative power in the numerator of a fraction can be moved to the denominator as a positive power, or likewise from the denominator to the numerator. So for example, if I have this fraction and I need to simplify it, well, that d to the -8 in the numerator, if I move that to the denominator, it will be a d to the positive 8. That h to the -4 in the denominator, if I move that to the numerator, it will become h to the positive 4. And so this is the expression now written with all positive powers. So for example, you might be asked to simplify something like this. Pause the video and see if you can simplify this, and then we'll talk about it. Well, of course, the first thing we'll do is we can treat the numbers separately from the exponents. And for the numbers, we'll just factor out the greatest common factor, which is 6. So not changing the exponents at all, just the numbers simplified to a 4 over 3. Now, with that x to the -4 in the denominator, that can move up to the numerator. One way to think about it is it moves up to the numerator, so we get an x to the 12th times an x to the 4th in the numerator. Another way is just to think about the law of division, and we get an x to the 12 minus -4. And of course, 12 minus -4 is the same as 12 plus 4. Of course, with the y's, we just have ordinary division of powers. So the y's, that's the easiest to handle. That is 9 minus 3 y to the 6. Then we treat those x's. We move it up to the numerator. This is one way to handle it. We move it up to the numerator. Of course, then we add the powers, and we get 4/3 x to the 16th y to the 6. And that is the most simplified we can make this. Here's a practice problem. Pause the video, and then we'll talk about this. Okay, So we have to rank things from smallest to biggest. The test loves these ranking questions. So first of all, 1/3 to the -8. Well, what does that mean? That's the same as 3 to the +8. Now remember that 3 to the 4th is 81. So let's approximate that as 80. 3 to the 4th is approximately 80. Well, 3 to the 8th is going to be 3 to the 4th squared. So that's going to be approximately 80 squared. And 80 squared, that's up above 6,000. So that's a relatively large number. That's what 1 equals. 2, 3 to the -3rd. Well, this is 1/3 to the 3rd, and so this is 1/27. Okay, so that's clearly much smaller than 1. And then if we look at the last one, 1/3 to the 5th, well, we don't even have to calculate the value. 1/3 to the 5th we know is going to be smaller than 1/3 to the 3rd. And so that means that 3 is the smallest, 2 is the middle, and 1 is the biggest. So in order, it's 3, 2, 1, and this is answer choice E. In summary, b to the -n equals 1 over b to the n. A base to a negative exponent is 1 over the base to the positive of that exponent. A fraction to the -n equals the reciprocal to the positive n, so we can flip over a fraction and get rid of the negative in the exponent. And exponents switch from negative to positive when we move them in a fraction from numerator to denominator, or vice versa. Now we can expand the laws of exponents a little bit further. Back in the arithmetic module, we learned about the distributive law. And really, the distributive law is one of the big ones. It's really one of the big mathematical ideas. And of course, the distributive law says that p to the m plus or minus m, what we can do is just multiply the p separately times each one of those terms. That is the distributive law. Multiplication distributes over addition and subtraction. As it turns out, division also distributes over addition and subtraction. Much in the same way, exponents distribute over multiplication and division. So if I have a times b to the n, or a divided by b to the n, I can distribute the exponent to each factor. So a times b to the n equals a to the n times b to the n. A divided by b, that fraction to the n, equals a to the n divided by b to the n. So we can distribute an exponent across multiplication or division. Here's a very quick numerical example. Suppose we have 18 to the 8. Well, we know that we could write 18 as a product. We could write it as its prime factorization. Of course, the prime factorization of 18 is 2 times 3 squared. So 18 to the 8th equals 2 times 3 to the 8th. Well, we can distribute that exponent to each one of those factors. We'll get a 2 to the 8th, and then we'll get a 3 squared to the 8th. And for 3 squared to the 8th, of course, we'll use the rule for the product of, for a power to a power, which means multiply the exponents, and we'll get 2 to the 8th times 3 to the 16th. So notice it's very easy to go from the prime factorization to of the individual number to the prime factorization of one of its powers. Here's a practice problem. Pause the video and then we'll talk about this. Okay, in the numerator, all we're going to do is multiply out that 4. We're just going to distribute it to each one of those terms. And for each one of those terms, we're going to have a power to a power, which means multiply the exponents. So we're going to wind up with x to the 8th, y to the 12th. Then we have we have to deal with the division. Well, x to the 8th divided by x to the 5th, we subtract the exponents, that's going to be x cubed. Y to the 12th divided by y to the -5th, that's going to be 12 minus -5, which is 12 plus 5, which is 17. And that's why we get x cubed y to the 17th. It's important to be aware of a very common and tempting trap because it's close to what is true. So now we're going to talk about a trap. First of all, it's legal to distribute multiplication over addition and subtraction. That's 100% legal. It's legal to distribute exponents over multiplication and division. That's 100% legal. But it's illegal to distribute an exponent over addition and subtraction. So that line, that's just the distributive law. That's 100% legal. That's one of the fundamental patterns in mathematics. This is it's also a version of the distributive law. We're distributing the exponent over multiplication and division. That's also 100% legal. The thing that is illegal is distributing the exponent over addition or subtraction. That is always illegal. And in fact, m plus or minus n to the p means that we're taking that, what's in the parentheses, m plus or minus n, and multiplying it by itself p times. So if these were variables, we'd have to FOIL out several times. So you'll never actually have to do that, but it's just important to keep in mind that that's what it would be, not multiplying, not raising the individual terms of those powers. And I'll say this is a very tricky one, because even when you understand that this third line is illegal, the human brain's inborn pattern matching software is tempted to make that mistake again, especially when you're under pressure. So you really need to know this cold so that even when you walk into the test and you're stressed in the middle of the test, you don't accidentally fall into making this mistake again, because it is a very tempting trap. Again, let's look at all this with numbers. Here is just the ordinary distributive law with numbers, multiplication distributing over addition. Here is the distributive law with powers, so that exponent distributing over multiplication and division. But it would be illegal if we had 8 plus or minus 5 to the third. That would not be 8 to the third plus or minus 5 to the third. And one way to see this is to just think, let's just take the subtraction case. If we look at 8 minus 5 to the third, well, what is that? Of course, that is 3 to the third, which is 27. Whereas if we looked at something different, 8 cubed minus 5 cubed, well, 8 cubed, as we've mentioned in other videos, is 512. 5 cubed is 125. If we subtract them, we get 387. And those two are not equal. So in other words, we get two different numerical answers, and that's why we can't set those things equal. We can do some legal math with sums or differences of power. First, we need to go back to that most impressive pattern in the distributive law. Now, this is very tricky. When we read this equation from left to right, we say that we are distributing p. When we read this equation from right to left, we say that we are factoring out p. So distributing and factoring out are two sides of the same coin. It's just a matter of whether we're reading this equation going from left to right or from right to left, but it's the same fundamental pattern. It's also important to remember that any higher power of a base is divisible by any lower power of that same base. Thus, in the sum of a higher power and a lower power of the same base, the greatest common factor of the two terms is the lower power, and this can be factored out because a lower power is always a factor of a higher power. So for example, 17 to the 30th plus 17 to the 20th. Well, first of all, we know that 17 to the 30th has to be divisible by 17 to the 20th. We know one is a factor of the other. And so 17 to the 20th is the greatest common factor of these two terms. So I'm going to factor that out. 17 to the 30th, I can write that as 17 to the 20th times 17 to the 10. By the multiplication of powers law, I can write it that way. And of course, 17 to the 20th, I can write that as 17 to the 20th times 1. I factor out 17 to the 20th, and I get 17 to the 20th times parentheses 17 to the 10th plus 1. And that is a factored out form of those powers. Obviously, the powers here are too large to simplify any of these resultant terms, but if the two powers and the sum are closer, sometimes such simplification is easy. So I will say, pause the video and see if you can simplify this, and then we'll talk about this. Okay, 3 to the 32nd minus 3 to the 28th. 3 to the 28th is a factor of 3 to the 32nd. In fact, 3 to the 28th is the greatest common factor of these two terms. So we're going to express both of them as products involving 3 to the 28th. So 3 to the 32, we can write that as 3 to the 28th times 3 to the 4th. And of course, 3 to the 28th, we can write that as 3 to the 28th times 1. Factor out 3 to the 28th, we get 3 to the 4th minus 1. Now 3 to the 4th, that's something we can calculate. 3 to the 4th, so one way to think about that is if you have memorized 2 to the 4th is 81. Also, 3 to the 4th is 3 squared squared. Well, 3 squared is 9, and 9 squared is 81. So that simplifies to 81. I do 81 minus 1, that's 80. And so this is 80 times 3 to the 28th. We don't often have to solve for something in the exponent because this usually involves much more advanced ideas than are found on the test. The test will expect us to know that if the bases are the same, if we have b to the s equals b to the t, then it must mean that the exponents are equal. That will be very important in the lesson Equations with Exponents, which we'll get to much later in the module. In summary, exponents distribute over multiplication and division, and those are the patterns. Exponents do not distribute over addition or subtraction. Those are very tempting mistake patterns. And we can simplify the sum or difference of powers by factoring out the lower power. And finally, if we have bases are equal and we have a to the m equals a to the n, we can equate the exponents. The units digit question. This is a very frequent question type on the test. Almost every quant section will have at least one of these. And it looks really hard. People who are not familiar with this question type, they see it, they panic because it looks impossibly difficult, but it's actually very easy. So for example, a typical question of this sort, what is the units digit of 57 to the power of 123? Now your first impulse might be, oh my, I need a calculator to figure out what 57 to the power of 123 is. Well, I'll share with you something. This is not something you'd be able to figure out on your own necessarily, but I'll share. As it happens, this number is 216 digits long. So in other words, no calculator in the world is going to be able to figure out 57 to the power of 123 for you. It turns out there are web applications. For example, if you're familiar with Wolfram Alpha, that's something where you could go, you could enter this, you could actually see all 216 digits if you were really fascinated with that sort of thing. But the point is, no calculator is going to help you with this. Now, at this point, this probably really blows your mind. Why is the test asking you to do something that no calculator on the planet can do? Well, let's be careful here. No calculator on the planet could figure out that entire power, all 216 digits, but we don't need all 216 digits. We only need the units digit. And it turns out that is a remarkably easy question. So first of all, I'll point out the general strategy that we're going to use. We're just going to look for a repeating pattern, and then we're going to figure out where that pattern will be at the desired power. So I'll have to explain this in more detail, but first of all, we need a really big mathematical idea. Here's the big mathematical idea. The units digit of any product will be influenced only by the unit digits of the two factors. Therefore, we only need to consider single-digit products when tackling a unit digit question. Now, this is a profound idea, and it takes some time to sink in. Let's think about this for a second. 3 times 6, we know, is 18. So we multiply a unit digit of a 3 times a unit digit of 6, I get a units digit of an 8. That means any long number ending in 3 times any long number ending in 6 will be a long number ending in 8. In other words, all that matters is the unit digits. The unit digits of the two factors is the only thing that determines the unit digit of the product. Now, if this is a hard idea to understand, what I strongly suggest is stop this video, pick up a calculator, and actually try this for yourself. Enter some numbers. Say, enter a number in the hundreds that has a unit digit of 3. Enter another number in the hundreds that has a unit digit of 6. Multiply them together. Time and time again, you will get some bigger number with a unit digit of 8. You'll always get that same unit digit in the answer. Then try some other combinations of digits. Unit digit of 2, unit digit of 7, or unit digit of 3, unit digit of 9, something like that. Just pick your own combinations. Do the single digit multiplication. So 3 times 9, for example, is 27. So unit digit of 3 times a unit digit of 9 will always have a unit digit of 7. Again, experiment with this and verify for yourself on your calculator that it works. If you're not a mathy sort of person, one way that you build intuition for numbers is actually playing with numbers and seeing these patterns. That's why it's very important actually to pick up a calculator and verify for yourself that this pattern works. This is the pattern we're going to employ. So, first of all, our big granddad question here, 57 to the power of 123. Well, first of all, the tens digit doesn't matter at all, so I might as well just consider powers of 7, because any number that ends in 7, when I take powers of it, it's going to have the same unit digit as just the powers of 7. Only the unit digit matters. So 7 to the first, of course, just 7. 7 squared, 49. I'm just going to write that as something 9. We have a unit digit of 9. 9, and then multiply by 7 again. 9 times 7, 63. So now we have something with a unit digit of 3. 3 times 7, 21. That's a unit digit of 1. So now we have a unit digit of 1. 1 times 7, we have a unit digit of 7. 7 times 7, 49. We have a unit digit of 9. 9 times 7, we have 63, we have a unit digit of 3. 3 times 7, 21, we have a unit digit of 1. And notice what results here is a repeating pattern. It's like mathematical wallpaper. We get 7, 9, 3, 1, 7, 9, 3, 1, 7, 9, 3, 1. It's just going to go on like that forever. It's a repeating pattern. The period of the pattern. Period of the pattern, how many steps does it take to repeat? Well, it repeats in a batch of 4. Every 4, it repeats. Now that's very important. It's very important to figure out the period of the pattern. Almost all these unit digit questions, incidentally, the period will be 4. If it happens that we're doing powers of 9, that has a period of 2. That makes things a little bit simpler. But if it's a period of 4, this is most typical for most of the unit digit questions you'll see on the test. The period will be 4. What that means is every time we get to a multiple of 4, when the power is a multiple of 4, we always come back to the same place. So 7 to the 4th has a unit digit of 1. 7 to the 8th has a unit digit of 1. 7 to the 12th, the 16th, the 20th, the 40th, the 80th, all of those would have unit digits of 1. That tells us how to extend the pattern, because 120 is a multiple of 4. So that means 120 will have a unit digit of 1, just like all the other multiples of 4. And then we just continue the pattern from there. After 1, we have a unit digit of 7. After 7, we have a unit digit of 9. After 9, we have a unit digit of 3. So that means 7 to the power of 123 has a unit digit of 3. And therefore, any number ending in 7 to the power of 123 would have a unit digit of 3. So that means that our friend here, 57 to the power of 123, has a unit digit of 3. And that's the answer. Notice that we had to do absolutely nothing beyond single-digit multiplication to answer this question. This question is always designed as a non-calculator mental math question. That's very important to appreciate. So the strategy for the unit digit question, focus only on single-digit multiplication. Look for the repeating pattern and determine the period. And again, most often the period is 4. and then extend the pattern using multiples of the period. This is the technique we use to solve these questions.